a category which is called the differential equation techniques. Now, quite obviously, you can expect that if one group of method is differential equation techniques, then naturally people will try to develop just the opposite to that. That is, therefore, is known as the integral equation techniques. And the first approach of this integral equation technique for field computation was done, or the methodology was proposed by a group of German researchers. They are from the Technical University of Munich. The history says something like this, that the Technical University of Munich is one of the foremost high voltage laboratories of the world. And during late 1960s and early 1970s, this lab was led by Professor Prince, who is called the father of high voltage engineering almost in the entire Europe. And some of the PhD scholars who were that time working for PhD under Professor Prince, three of them, one is Professor, I would not say professor, one is Hans Steinbigler, the other one is Hermann Singer, and the third one is Paul Weiss. Later on, they all of them became very well-known professors. Hans Steinbigler became the professor of Technical University of Munich. Hermann Singer became the professor of Technical University of Hamburg. And Paul Weiss became the professor of Technical University of Aachen. Now, during 1969 and 70, like that period of time, they were all very active researchers. And it is because of their effort, particularly Hans Steinbigler was the pioneer in developing this methodology. And it is his PhD thesis where he has outlined all the formulations of charge simulation method. And all this work was partly by Hans Steinbigler, then Hermann Singer and Paul Weiss, and then together they wrote a paper which was published in IEEE Transactions on Power Apparatus and System in 1974. And that laid the foundation of the growth and development of the charge simulation method. Now, I can just tell you one thing, that the importance and the quality of any publication, any paper by any scientist or any researcher is judged by how many other people are referring that particular work. That's one of the major index of the impact of your work on the scientific community. I can tell you one thing, that this particular paper of 1974 by these three German researchers, anybody who does any work on electric field computation, I have never seen that they are not referring to this paper. So I don't know what is the citation number or all those. That's a phenomenal number it should be. So that's how all it began. But why I am telling all this story, just to we will go into the subject, but sometimes some stories, histories, how the method developed, that is also, at least for me, it is very important, and I am always interested into that. Now, this charge simulation method is very close to my heart. Why is it so? Because I did my PhD on that. I was doing my PhD in the late 1980s. So I started around 1986, 87. And that time I started working on charge simulation method. Now, I completed my PhD. I submitted my PhD in 1992. And then in 1993, I received my PhD degree. And after that, I applied for a very well-known postdoctoral research fellowship called Alexander von Humboldt Fellowship in Germany. Now, as luck would have it, I got it, and I went in 1995 to Technical University of Munich in this very high voltage lab. And at that time, Hans Steinbegler, who proposed in 1970s, early 70s, the charge simulation method, he was very senior professor there, and he was my supervisor, or I mean host. They call it host at the Technical University of Munich. And it was a great luck for me because I was then direct student of this very well-known scientist. Let me try to show you something from my all this story and try to show you a photo. I hope it is coming on your screen.
Yes, sir.
Yes. Now the interesting thing is, uh, it will be very difficult for you probably to recognize me at that time. That's me, in fact. So this is 1996, and 1996 summer. They had a party in their institute in the afternoon, or rather evening, summer party. So that's why you can see people. This is the backyard of the high voltage laboratory. And on the photo, who is on my right with a t-shirt is Professor Hans Steinbegler. And on my left with a tie and white shirt is Professor Wolfram Boeck. By the way, Professor Boeck was one of the most famous researchers in the world about in the SF6 area. In all sulfur hexafluoride insulated equipment, he was the top scientist of the world. And so I was very lucky to be with them in very practical areas. People were all working. So, and then when I went there, I was supposed to work on an area, but then Professor Steinbegler changed my area, and I worked on what is today you call it, or people call it, boundary element method. So I had to learn boundary element method, and that's another story. So, but boundary element method is not in your course, so I will not go into the details of boundary element method. Now, this is a photograph from 1996, and I tell you that these people developed all these things in early 1990s, 70s. So they were already very senior people at that time. Professor Boeck is no more. He went to his 70 award some 3-4 years back, but Professor Steinbegler is still there. I think he's nearing 90. Now, one more interesting point I'd like to tell you that when this group of people were working under Professor Prince and developing CSM, there was another group of researchers working in the same lab, that is this PUM lab under Professor Prince. And there was another very famous, later on very famous person called Hermann Dommel. Now, Hermann Dommel developed another method, which was at that time another fundamental one, and later on became very famous. And even today, all sorts of softwares are based on that. That is called EMTP, the Electromagnetic Transient Program. All sorts of transients that is being analyzed and softwares that you use. The fundamental basics principle is based on that EMTP. I don't know whether you have heard this name or not. But if you have not heard this, remember this name, electromagnetic transient program, EMPP. It is actually the basics of all the programs which analyzes the transient. For example, you might have heard the name of SPICE. I'm sure you might have SPICE or SPICE, which does this sort of transient analysis. The fundamentals of that is based on EMTP. Now, I just sometimes, I mean, when I was there, all these things were there on their wall, lot of citations and others. So I sometimes wondered that what a golden period. You just think of it that at the same time, some people are developing charge simulation method, which is a fundamental contribution and which will impact science for next 50 years. And then another group of people at the same time developing electromagnetic transient program, which is even today the basics of so many software. So this is really a golden period of scientific developments. So with this, I stop this one and I come to my topic, that is your class. So let me now see where it is. Yeah. So let me show you straight away to that file. Okay, so now I am going to share it. Hopefully now it will come on your screen. Is it coming now?
Yes, sir.
Good. Thank you. So now let's move on to our course. Uh, this history part I have already talked about. So now I straight away go to the formulation. That what is the basic formulation of the chart simulation method? So the first very important point to note about this method is that it is not based on any differential equation technique like Laplace's equation or the Poisson's equation. The basic approach here is again different. So, as you remember that I explained FEM, where the basic approach was that the field is computed based on the fundamental aspect that total energy stored in the field should be minimum. Now here in CSM, the basic approach is completely different. Now let me ask you one question, just a very basic question. Say in any interview, if the interviewer asks you that, tell me one quantity, if that is not present, there will be no electric field. What will be it?
Charge.
Right, very correct, electric charge. So field is not produced by electric potential or current or so on. It is all related to charge. So if electric charge is not there, there will be no field. And you also know that if, let's say it's a conductor, and you all have studied, right? If it is a conductor, where do the charges reside?
Inside the metal element.
No. I mean,
The conduction band.
pardon?
So in the conduction band.
Where will be the charges? I think you know, you have studied this even in class 12. Where are the charges in the case of an electrode? You don't remember?
So in the conduction band.
No, I'm not going into the band or others. I'm just physically saying if it is a charge sphere, is it, I mean,
The
if it is
outer
a,
surface.
Outer surface.
correct. Now you are absolutely correct. It is on the surface of the conductor. Acha, why is it so? Why it is only on the surface? Why not in the volume?
The inside electric field is zero.
Well, this is actually a derived pattern. Any other, I mean, there has to be a physical explanation, right? Why the charges are on the surface. It could have been in the volume itself. let me explain it in a very simple way, right? So without going into all the equations and others. There was a famous saying by Albert Einstein. When people were all talking about theory of relativity and this and that. Once he said that if I cannot explain a topic in simple way, it means that I have not understood the topic. And I fully believe in that. This is a wonderful statement. Because if I have understood any subject, I should be able to explain it in a simple way, not by through any complicated manner or a big equations. So let me explain it in this way. Look at the diagram. Let's say this is the electron, and it's a solid one, let's say, and it's a conductor. And you all know that within a conductor, the charges are free to move. That we all know. Now, if that is the case, if the charges are free to move, then if we have opposing polarity of charges within the conductor, then what will happen? They will move and then recombine. So there will be no charge. But we all know that there will be charge when we have a charged electrode. So therefore, we can say logically that there cannot be opposing polarity of charges within an electrode. It could be either positive or negative, but not both positive and negative. Because in that case, they will recombine. Now, when there is a same polarity of charges present within the volume of an electrode, the Coulomb forces will be active, and Coulomb forces are repulsive in nature. Repulsive means what? Repulsive means that the distance between the two elements must increase. That is the idea of repulsion. Attraction means the distance between two elements or particles should reduce. So when Coulomb forces are acting in repulsive nature, then all the charges are trying to go away from one another, move away from one another. So instead of going towards the center, all the charges are trying to go out. So what happens? Finally, they reach the surface. At the surface, what happens? Because at the surface, it is surrounded by an insulator. It can be like air, it could be transformer oil, whatever. But this is an insulator, and within an insulator, charges are not free to move. So what happens on these charges comes to the surface of the conductor, and then it finds that there is an insulator, I can't move. And therefore they are on the surface. Now you can always logically extend this and ask me a question that if all these positive charges or negative charges are on the surface, still Coulomb forces are active. The answer is yes. Then why not this electrode is experiencing a force? The answer is yes, they are experiencing a force. All charged electrodes experience a force because of the Coulomb forces. But then next question you can ask me that we can see that force. We can see so many electrodes like these transmission conductors, these, that, but where is that force? The answer is the force magnitude you have to calculate. And we can see that whether it can really have any influence on the metallic conductor, which is mechanically very strong. But let me tell you now, if this conductor is not metal, if it is some sort of a, say, biomaterial or something, then definitely this will play a role and the shape of the electrode may get changed. So the research on the other direction, they have to consider this when it is very, what is that called? Film type electrode, not the electrode like a copper or aluminum conductor. So these are some of the things, but based on these, we can first of all say that the field is produced by the charges which are on the surface. These are the actual charges present. So the concept that was proposed was so simple that it was almost like why people have not thought of it earlier. They said that let's simulate these charges. And how do we know these charges? The answer is no. We don't know the charges on the electrode. Only one thing we know, what is the total amount of charge. That can be calculated, but not at any point what is the charge. Second is, are they uniformly distributed over the surface? The answer is no. They are not uniformly distributed. So therefore, what can be done is that let us assume, as you can see here in this figure, this cross, they are some fictitious charges. So I repeat, they are not true charges. They are fictitious charges. We are, bringing it into our system for computation. And for every fictitious charge, I assume one point on the surface, which is also called a contour. So this cross is called the charge point, as you can see at the written, and the dot is the contour point. So if there are n number of charges, then there will be n number of contour points. That's the beginning or the starting point of charge simulation. Fine, but then how do we proceed? So everywhere you remember that in FEM or FDM, what we did, we discretized the system and created the nodes. So here what we are doing, we are discretizing the contour itself because the entire contour is subdivided, and we are creating the charge points and the contour points. That's the part of the discretization. So straight away, can you see a big difference? What is that? In the FEM, you are discretizing the entire region of interest. Whereas in CSM, you are discretizing only the contour, that is the surface. And that's a big difference because now your discretization has reduced significantly. And particularly the problem that we face in FEM, that if it is extended up to infinity, then how far we will discretize. Now here in CSM, there is no such problem because we will discretize only the surfaces present in the system. It could be conductor surface, it could be dielectric surface, but only the surfaces. So one major aspect is here that discretization is much, much lesser. Second point, when we discretize, certain things are known. That means when we make the FEM mesh, we know the coordinates. Exactly here also, when we discretize, we know the coordinates of these charge points, that means the location of the charge, and the contour point, that is the location of the point on the contour. That coordinates are known. Otherwise, we can't compute the field. What else is known? One more thing is known. That is the type of charge. That means what type of charge I am placing here. Anybody who have studied field theory a little bit well, you know that there are a lot of charge configurations which we use in field theory. The basic one is point charge, but there could be other charges like line charge, etc. I will give you some idea later on. So two things are known, that is charge type and charge location. Then what is unknown? Unknown is the charge magnitude. Because as I said, what is the charge at different locations, we don't know. Therefore, the charge magnitudes are not known. So it is like Q1, Q2, Q3, and they are our unknown variables in this case. The moment I say that, then if there are n number of charges, I can see that there are n number of unknown variables. And now I have to solve it. How? Now we apply our very well-known condition. What is that? Because this is an electrode, it will have a well-defined potential. Because electrodes are equipotential. And this potential, which quantity is defining this potential? The actual charges, the true charges on the surface. If I say that the effect of all the fictitious charges taken together at any contour point is equal to the potential of the contour, which indirectly means that the potential of the contour is defined by all the charges on the surface which are actual charges. And if the potential at the contour is same as that potential, but now it is defined by the fictitious charges, then we can say that the effect of the true charges is being simulated by the fictitious charges, because the net effect is same. That is the potential of the conductor. That is same. So that is the approach. For that, what we do, this is the equation we write. So what is Pij 16.1? Pij stands for, like in this equation, you can see that charge points, they are marked by subscript J. J varies from 1 to n if there are n number of charges. Contour points are defined by subscript I. I also varies from 1 to n because for every charge there is one point. Pij stands for potential at the contour point I due to unit charge at location J. So I repeat, slowly I repeat. What is Pij? Potential at contour point I due to unit charge at charge location J. So if I say any charge location J and any contour point I, then I can calculate Pij how? From the type of charge. Because if it is point charge, I know from the coordinates how to calculate that potential. Similarly for line charge, etc. So Pij can be done, we can have equations for Pij. And if I multiply Pij by the charge magnitude at that location, that is Qj, I get the contribution at that contour point I towards the potential by that jth charge. So I repeat, if Pij, this is known, then Pij multiplied by the Qj, which is the magnitude of charge at the jth location. What is that? Pij into Qj. That is contribution of that Qj towards the potential at the ith contour point. Now, if that contribution is added for all the j number of charges, I get the potential. So we write that summation of Pij Qj, j varying from 1 to n, that must be equal to phi. What is phi? Here you can see phi is the potential of the electrode. Therefore, this becomes the fundamental equation of our CSL. This is for single dielectric case where we are not considering any dielectric medium. Then how do I solve this? Well, very simple. This same equation I now apply for all the contour points. That means now I vary I from 1 to n. So this is equation for one contour point, equation 16.1, where for a given value of I vary j from 1 to n. Now, if I vary I from 1 to n, this equation, how many equations I will get? N number of equations. And that is exactly 16.2 I have written. So you can see P11 into Q1. See, this is like j is 1 and I is 1. Then P12, Q2. So j is 2, I is 1. So the first row is for the contribution of all the charges towards the contour point 1. And when we add that, it must be equal to the potential phi. The second row is the second equation. For this is I is equal to 2. Then I vary j from 1 to n and sum up all the contributions. It should be equal to phi. In this way, I write equations up to I is equal to n. So I get n number of equations. And if you now look at this equation, there are n number of rows and every column represents one charge. There are n number of charges, so there will be n number of columns. So when I represent it in the matrix form, I get the coefficient matrix and it is an n by n matrix. Then these charge magnitudes are unknown. It's a column vector of size n or length n, and the right hand side is the electrode column, potential column vector also of length n. The right hand side is known. Within the coefficient matrix, these Pij's are known because, as I said, that if I know the charge location, contour point location, and charge type, I can have from the coordinates this Pij, just like the FEM. And therefore, I can solve this matrix. I get the values of Q. So the unknown variables are known. And beautifully, you can see that once again, I have, or rather, the CSM have developed a system of equation which is linear equation, and it involves only scalar quantities. Exactly the same as FEM or FDM. Finally, all the methods, FEM, FDM, CSM, and even boundary element method later on, they finally develop a system of equation which is a linear system of equation, and it involves only scalar quantities. That's the beauty of the methodology. Another very interesting aspect that you can see from this one is that these Pij's are all related to coordinates of charge and point. So therefore, they are not zero. They have certain expression. Depending on the coordinate, I can calculate this. So this coefficient matrix, which is an n by n matrix, there is no zero term, which is completely in contrast to FEM and FDM. I have explained earlier that FEM and FDM, they have mostly zero elements, and that's a sparse matrix. Whereas in CSM, it's a full matrix. It's a fully occupied matrix. Every element is having a certain non-zero value. So that's, you can clearly see that they are these methods, that is FEM and CSM, they are diametrically opposite to each other. And therefore, these two methods, they approach the solution of the problem from completely two different angles and get the solutions. Now you can, next logical question is, well, fine, we have solved this and I have got the potential, because once I get this, then at any, and the next beautiful thing is that once I know Q1, Q2, Qn, etc. Now going back to this, that the potential at any point, that's definitely created by the actual charges on the surface. But now we have simulated the effect of the actual charges by the number of fictitious charges. So any point in the region of interest, if you have to calculate the potential, the method is exactly equation 16.1. That means just find out the contribution of each charge and sum it up. And then you right hand side, that means after the summation, you get the potential of that point. So at any point in ROI, that simply is you take the contribution of each point, Pij into Qj, sum it up, get the potential. This is called the post-processing. That means once I know the Qj, I find out the potential of any point straight away. Now, another question that you should ask me that, well, fine, I have understood everything, but tell me why these charges are placed inside the electrode? Why not outside the electrode? That's a valid question you can ask me. So I have to explain it to you. Now, if I put these fictitious charges outside the electrode, then these charges are within our region of interest, because outside the electrode is my region of interest, not inside the electrode. If these charges are outside the electrode, then that particular point where the charge is located is also within my region of interest, and we want to know the field at that point also. But the big problem becomes that If I take that point where the charge is located, the distance between charge and the point becomes zero. And you know that all field equation, the distance, that quantity is always in the denominator, not on the numerator. All expressions for charge. So I can't compute the field at that point. That means if there are n number of charges which are outside the electrode, then there will be n number of points where I will not get the result. I will get results at all other points. But that's a big problem because within my system there are n number of points where I don't get the solution. In any problem where we face this problem that I am not getting the solution at certain number of points, what are these points called? Do you have any idea from your knowledge of your earlier mathematics or whatever? That in our system, I am unable to get the solution at certain points. These points has a name. Exactly, wonderful. These are called points of singularity. And any method that gives rise to point of singularity is a poor method. There should not be any point of singularity in solution. But if I put these charges outside the electrode, we are generating n number of singular points. So we should not do that. That's why the charges are placed inside the electrode, because that's not within my region of interest. So that's another aspect to that. And as I said, that once the solution is done, if I want to know the potential, I calculate the contribution of the each charge, that is Pij into Qj, and I get the potential. But then next question is, only potential is not enough. I must also know electric field intensity. But how? Well, electric field intensity, how do I get? I mean, mathematically, how do I get electric field intensity? It's the first order derivative of the potential. That is the potential gradient. That is electric field intensity. So how do I get? So very simple answer. I take the first order derivative. That means if I mean, by the way, here we take three components separately. That means x component, y component, and z component. If it is in the Cartesian, if it is in other coordinates, it will be different. So what I do is, instead of taking Pij which is the contribution for potential, here we take minus del Pij del x. Because minus del Pij del x is, you know, that is the electric field intensity. Del Pij del x is potential gradient, and electric field intensity is minus del Pij del x. That's the x component. So what I say is that this minus del Pij del x, we call it the field coefficient. Pij is called the potential coefficient. This del Pij del x is called Fxij. That means what is the field intensity in x direction at the ith point due to a unit charge at jth point. That means, once again, Fxij, which is nothing but del Pij del x, is what is the field intensity and in its direction at the ith point due to unit charge at the jth point. In the same way, then I take Ey as minus del Pij del y, then Ez minus del Pij del z. Now, if I know the del Pij in terms of the coordinates, then del Pij del x is simple partial derivative. We can do that and we can develop this equation. So this 16.4, 16.5, 16.6 straight away gives us the solution. But now a big question comes. What is that? See, this is an electrode, but in our world, such isolated electrode is only a theoretical approach. Because there is always a second electrode everywhere present. Can you tell me what is the second electrode which is present everywhere?
Earth.
It's absolutely correct. It is the Earth. Because Earth is always an equipotential of potential zero. So it's an electrode. And field generated by any other system is invariably affected by Earth. So we can't ignore Earth. I mean, whatever we do, we can't ignore Earth, the effect of Earth. But Earth is such a big, electrode. So if I have to simulate that, we will have infinite number of charges. That's not possible. So you have to think about something else. That how do I, take into account the effect of Earth's surface? For that, you probably know that in field theory there is a very well-known approach to take into account the effect of Earth's surface. That is called the method of image. That means for every charge, we consider an image charge. And how the image charge is defined? That means its magnitude will be equal and opposite to the actual charge, and its location will be exactly the same depth as the height of the actual charge from the surface. So whenever in CSM, we take this fictitious charge, the Earth surface we have to consider and height from Earth surface we have to consider. We take the image charge of opposite polarity. That means if it is Qj, then it is minus Qj. And the coordinates of image charge we can automatically find out from the coordinate of the fictitious charge. So therefore you can see actually we have to deal with not just n number of charges but 2n number of charges, but fortunately their magnitudes are only n. That means Qj. Other one is minus Qj. So it's not a separate variable. So number of variables remain same. So whenever we write this equation, is 16.1, whenever we write Pij Qj, we also have to add another one, that what will be the Pij minus Qj. That means the effect of the image charge. That will be always coming together. Without the image charge, if you take CSM, it will give you completely wrong result. So that's another very significant aspect of this CSM formulation. There are something called floating potential electrodes. That means which are charged, but its potential is not fixed by some source. There are a lot of examples to it, particularly the electric shields, the field shields, or field that field control rings. These sort of things are typically floating potential electrodes. And there is another very basic example of floating potential electrode is in what is called condenser bushing. By the way, have you studied condenser bushing? Yes or no?
No, sir.
No. Oh, this is very unfortunate. Actually, I thought somewhere in your course, condenser bushing should have been touched upon. This is so important in our practical life, irrespective of high voltage or others. Condenser bushing is the most efficient bushing in our electric power system. So these condenser bushings, they always have the floating potential electrode. Now, how floating potential, as I said, that I don't know the potential because it's not known. So then how do I write the equation? Well, any electrode is an equipotential, so potential of all the points must be same. So we put the equation like this, 16.7, that is phi I plus 1 minus phi I is 0, because both the potentials are same. So if I have a number of points on the floating potential electrode, if I apply this equation, can you tell me how many equations I get? If I apply this equation 16.7 to n number of points on the floating point electrode, how many equations I get? It will be always one less than the total number, because our equation is phi I plus 1 minus phi I is 0. So if you apply, you will get n minus 1 number of equations. So there has to be a supplementary condition included here, which is that in the floating point, floating system, uh, although it has some system-induced, potential, but the net charge will be zero. So we put an equation that within that floating point electrode, Q1 plus Q2 or whatever, Qi plus Qi plus 1, that will be equal to 0. So n minus 1 equation, as you can see in this matrix formation, and then one supplementary condition makes it an n by n. So then you can solve it. There is one more supplementary equation that if at all we know what is the charge, then we can of course put summation of the charges is equal to the known charge. So that could be also possible. So depending on our system, where I am going to compute the field, I can do it. Multi-dielectric today I will not discuss, I will discuss in my next class. What I will discuss is this one, the types of fictitious charges. I already talked about this, that when I was telling you, the most common charge configuration which you have studied from your school level is the point charge. And of course, point charge we use in CSA. But just using point charge, if I want to solve all the cases, that will be very difficult. So we bring in a lot of other charge configurations. One is the called line charge of infinite length. That means the charge configuration is a line charge, but its length is infinite. Now you can ask me, where can I use it? That means to simulate what? Two examples I can give you straight away. One, the transmission line conductor. The transmission line conductors, I mean, if you take the distance between two towers, it is typically varying between 120 meters to 150 meters, which is quite long compared to the diameter of the conductor. So considering the diameter of the conductor, the length of the conductor is almost infinite. So if I want to just simulate the transmission line conductors, the best way to use not point charges, because then you will have very large number of point charges. To use line charge of infinite length, and I can simulate it. In the same way, if you take the case of a cable length sometimes goes even up to kilometers, whereas the cross section remains same. So compared to the diameter, the length is infinite. So if I want to simulate the cable, then I have to put the infinite length line charge. That makes the simulation much more efficient, and the number of charges, matrix size will be smaller. But for example, if I take the cable and if I come towards a joint where the cable termination happens to an equipment, now at that point of place, I cannot take the length as infinite, because then the cable uh, configuration changes at the termination. So in that case, for a certain finite length, I cannot make it say that the field will be simulated by infinite line charge. So in those cases, we need finite length line charge. This is also true if I have a cylinder of fixed length. There we will use finite length line charge. So we have now point charge. We have now line charge of infinite length. We have now line charge of finite length. Then a very interesting charge configuration is there, because this geometrical shape is uh, so versatile, so powerful. It's the ring. When you think about it, you visualize it. If you take one ring, put it on a table, and if you take now very large number of ring of same diameter, and you put one ring on top of the other, What you get?
Cylinder.
Cylinder, right? So now we can see that a cylinder can be simulated by rings. That is now quite clear. Excellent. Now you think about it. Acha, you think about a cone, and if I cut the cone by a horizontal plane, every time I get a ring, isn't it?
Yes, sir.
So from base to the vertex, how is it actually made? That means we are putting rings on top of the other, but with reducing diameter, isn't it? So that means I can simulate a cone by rings. So I can simulate a cylinder by ring. I can simulate a cone by ring. So can I simulate a sphere by ring?
Hollow sphere.
Hollow spheres, yes. So I
Yes,
can do that.
yes, sir.
So our spherical electrodes are hollow spheres, isn't it? They are never solid spheres because charges are only on the surface. So we don't use solid spheres. So then you can see it's a cylinder, sphere, cone. They can all be simulated by rings, and you can see there are many others also. In fact, any axisymmetric configuration which is rotationally symmetric can be simulated by ring chart. If you visualize, you can clearly understand that. Another very interesting example is called a toroid. You understand what is called a toroid?
Yes, sir.
Have you seen any toroid in your normal life?
Current transfer.
Oh my God, that's a too complicated. A very simple example. See, this is called. I always tell that you have to observe carefully. Very simple thing. You tell me what is a toroid. Current transformer. How many people have seen? Acha, how many of you ride bicycle? Anybody? No? Yes? No?
Yes, sir.
Acha, is there anything called a tire tube? What is that? That's a toroid, isn't it? So in this way, now in the moment I say it, then you will be able to understand there are a lot of toroids in life. Yeah, we wear the bangles in our hand. What is it? Is it isn't it a toroid? Yes. Acha, how do we generate toroid? Can we generate toroid by a ring? Yes or no? Can we generate toroid by a ring? The answer is yes. You take a ring, take an axis, and rotate the ring by 360 degrees. You get a toroid, isn't it? For example,
Yes, sir.
this. So you can see how powerful this ring is. Now you can slowly you can understand that how powerful this ring is. So we take the ring charges and we simulate lot of system by ring charges. For example, if I have to simulate a sphere, no question of that, we will use ring charges, and then by a small number of charges, I will simulate the sphere. So I will just show you one or two diagrams so that you can get a clear idea about this simulation. So let me show you. I hope now you will be able to see it. This is another file I am showing you. Can you see it now?
Yes, sir.
Yes, sir.
Yes, sir.
Yes, good. Now, see, uh, let me make it slightly less. How is it? Control minus, no? Oh, God, whatever. The mouse, no? Ah, correct. Ah, I'm trying to fit it on the screen. Yeah, now you can see probably the whole thing. See, what is this configuration? There are two spheres. This is typically our sphere gap. In our lab, you might have seen the sphere gap. This is typically the sphere gap. So two spheres, and they are supported by a cylinder because I have to support the cylinder sphere. No? So there is a cylindrical component and the spherical component. So how I am going to simulate it? The answer is very simple. See, the sphere, this cross, you can see here. No? These are the ring charges. And this is a rotationally symmetric system. So this is the axis of symmetry. And this cylindrical part, this is not of infinite length. This is finite length. So there are some finite length line charges here. Top and bottom you can see. And the tip of the sphere, which is just a point, now that one I cannot simulate by a ring. So tip of the sphere is I put 1 point charge. Here you can see 2 point charges to simulate the tip of the sphere. So the entire spherical body is simulated by ring charges. Then the cylindrical parts are simulated by the line charges of finite length. And the tip of the sphere is simulated by 2 point charges. Let me see another diagram. Yeah, this is a very, very practical diagram. Once again, I have to fit it. Oh, what is it? Two figures are there. In one page. Ah, yes, now I think you can see it. What is it? This is actually a bushing. Now, this is a very actual bushing, so it's a complicated one. What is it? You know, bushing is something which actually there will be a live conductor at the center of the bushing. That's the red one. So that is straight away cylinder, the central red part. Now, that is not of infinite length, so it is a cylinder of finite length. So we will put some finite length line charges. As if you can see my mouse moving, this is the red part, the finite length line charges. Then there are a lot of boundaries here, but they are all rotationally symmetric. So we put the ring charges. So we simulate them by the ring charges. I will not go into all the boundaries because I have not discussed about the, what is that called, multiple bound dielectric cases. So I will not go into that. Here again another example. This is an insulator. At the top I have a disc type electrode. At the bottom I have a disc type electrode. It is a rotationally symmetric system. Therefore, the electrodes are simulated by ring charges, this cross. But then the central point at the midpoint of the electrode, which is lying on the axis of symmetry, we simulate by your point charge because that cannot be simulated by a ring charge. That's right on the axis. So even if you rotate around the axis, it remains a point. It's no longer a ring. So we put a point charge, 2 point charges at the axis of symmetry. Rest are ring charges. And then you have the insulator contour. Since it is rotationally symmetric, so I can use ring charges, because if you cut this geometry by a plane which is perpendicular to the screen, you will always get a ring of various diameters. So we have put all this cross, they are the ring charges. So in this way, we simulate the systems in charge simulation method. So therefore, today I am going to stop here. Next class, I will take up the next important aspect, that is the multi-dielectric simulation. So if you have any questions, Otherwise, we'll close the class.
Practically, charges are moving,
Charges are moving.
so they
Yeah,
are considered fixed charges.
yeah. But see, charges are moving only when there is a current part involved, right? If there is no current is not involved, charges are not moving. What I am discussing, I have stated at the very beginning, it is the electric field, not electromagnetic field. If the charges are moving, then things are different. It's called electrostatic field, what I am discussing. Because in our high voltage system, we hardly consider current because, you know, currents are very small in high voltage system, the insulating system. Any other question? Okay, then you can log off. Okay, thank you.